Hello, Mr. Simpson here with our next video in Chapter 16 on galvanic cells and cell potential. Please pause the video and copy down the learning objectives. So to start Chapter 16, we reviewed oxidation, reduction, chemistry, redox reactions. So in general, any spontaneous redox reaction can produce electrical energy because you get an exchange of electrons. Something is losing electrons being oxidized, and something is gaining electrons being reduced. So if you remember the mnemonic oil rig, oxidation is losing electrons, and reduction is gaining electrons. So if we isolate that or compartmentalize that into two half reactions, as we've seen our half reactions into two half cells, we can isolate that flow of electrons. Okay, an important addition here to our oxidation is losing electrons is that is occurring at the anode. Oxidation is occurring at the anode. So I like to think about, I remember that by thinking of the O and the A. The vowels go together. Oxidation at the anode, and reduction will happen at the cathode. So the R and the C. The consonants go together. That's how I like to remember where that's happening. So we are going to take a look at what a galvanic cell looks like, how it works, and then calculate some cell potentials. We look at a cell diagram here in a second. There's one more important piece of information that completes the picture, and that's the salt bridge. I'll show you what it looks like in a second, but if our anode is losing electrons continuously, then it's also going to be adding positive ions into solution. And so in order to account for those positive ions, we need to add negative anions to some degree to kind of complete the circuit, if you will. So that's where the salt bridge comes in. Okay, so here is an example of a galvanic cell. So over here, we have our copper anode. So this is where oxidation is occurring. So electrons are being lost from the copper. If I connect with a wire here, this flow of electrons will go through the wire, and then if I have an external circuit, this is where the electricity can be seen. The electrons will flow here to the cathode. So the cathode, in this case, the silver, is being reduced and gaining electrons. Right. So as this copper is losing electrons, then the copper ions, the copper cations, are going into solution here, the Cu2+. That's where the salt bridge comes in. You saw in the notes typically an ANO3 or KNO3. So what's happening here is anions are going to flow this way towards the anode, so that we get this this solution being formed here between the copper 2 cations that are being put in solution and now the anions. That helps to, as I said before, complete the circuit. We have just the other thing happening in the other direction. We have our silver nitrate solution. So we have our anions here, and so our sodium will come into solution here because our silver ions are coming from solution into and depositing on the cathode here as the reduction is occurring. So that's how you get that complete circuit, and you can see the important role here of the salt bridge to account for the additional cations on the anode side and the removal of cations, so the additional anions on the opposite side. Now, it's unrealistic to draw out a large cell diagram like this every time we are talking about a particular galvanic cell. So we use what's known as cell notation. You can see what that looks like here. So you can see here it always goes anode to cathode because that's how the electrons flow. So over here, whatever's written over here is our anode, whatever's written over here is our cathode. We put our solution that is present here. Often they'll give you the concentration of solution, although they don't have to. Okay, so this is oxidation. Because that's our anode and this is reduction. And so I can get a sense here, looking at this, what the two half reactions are going to be. Additionally, we have some lines here separating here. So this is a phase boundary. By phase boundary, we mean the difference between liquid and metal. So, the idea here that we have a metal anode in a liquid solution. So those two things, The metal and the solution are separated here by a single line, and then this double line represents the salt bridge. So you can see it's separating our two half cells here. The salt bridge, a double line in the middle. Okay, so we should be familiar with that cell notation, either writing it, producing it, or taking a look at it and then being able to separate out the two half reactions. Now what we want to be able to do here is calculate the electrical potential, or in this case, since we're talking about a galvanic cell, the cell potential. You can see here the calculation is pretty simple. Okay, so the cell potential, which is denoted by this symbol here, is just the potential of the cathode minus that of the anode. The tricky part here is going to be determining what is the cathode and what is the anode in a particular reaction, and I'll walk us through a couple example problems here in a second. Before we get to that, I want to show you a pretty common table. You'll find this in your textbook and also in the PowerPoint. If I had more time, we would get into the notion of the standard hydrogen electrode, but all these reduction half reactions and reduction cell potentials are based on the hydrogen atom here, which is 0, and all of these, either go up or down from there. We don't need to worry about that at this point. We just want to be able to pull the data off this table. So you can see all of these are set up as reductions, all right? So gaining of electrons. So an ion gaining an electron and forming, the atom, whether it's solid or gas. All of these are listed as reductions. Now, if the reaction is in fact not a reduction, we don't have to change the sign or anything as we flip the reaction around. We're just always going to pull these off like this. But the value of these may in fact be the key that helps me to determine which is the cathode and which is the anode. More on that in a second. Here's our first type of practice problem. So why don't you pause the video and copy this down. All right, in this first type of example, we are given a net equation for a voltaic or galvanic cell. Those terms are interchangeable. We are asked to identify the half reactions, what's being oxidized, reduced, what's the end of the cathode, and ultimately to calculate the cell potential. So based on this type of problem where they give me the reaction first, I can work to take a look at what the reaction is to write my two half reactions. So clearly over here on the reactants, I have a solid, so that means I'm going to produce my cation, and that means I've also produced an electron. That was right, sorry, 2 electrons. The other half reaction here, we can see we start with my cation, which means I'm going to be gaining 2 electrons to produce my metal. Okay, so based on taking that net equation apart and writing it as 2 half reactions, I can see here that this is the oxidation, all right, losing electrons, and this is the reduction, gaining electrons, okay? And then from there, I know that oxidation occurs at the anode and reduction occurs at the cathode. So I've essentially answered all the parts to this question here. Write the 2 half reactions involved. I've done that and identify each term as oxidation, reduction, anode, cathode. Now that I know that, now I can do my calculation where I calculate my cell potential. All right, is going to be that of the cathode minus the potential of the anode. So I would go and I would look these reactions up in that table I showed you, and I would find those values to be 0.7996 minus a negative 0.1375. And we get a value here for our cell potential of 0.9371. All right, one additional important piece of information to note here, that if I have a positive value for my cell potential, that means the reaction is spontaneous. All right, positive cell potential means I have a spontaneous redox reaction. Okay, so let's look at a different type of cell potential problem here. Go ahead and pause the video and copy this in your notes. Okay, so you can see this one's a little different. I do not have a reaction, so I cannot determine the half reactions and determine what is being oxidized and reduced in that fashion. I do not have a cell diagram or cell notation to determine what is oxidized and what is reduced. I just have two half reactions. Now, when this is the case, if I look up those reduction potentials in my table, for this first one, I get 0.34, and for the second one, I get a negative 2.868. Okay, when I have to approach a problem in this fashion, then the cathode, where the reduction takes place, is going to be the more positive potential. Okay, so the fact that this is 0.34, positive 0.34 as opposed to a negative 2.868, that tells me that this is the cathode, because that's where reduction is occurring. That means this is the anode, and again, that's where my oxidation is occurring. Okay, so this is the other way in which I can identify those two important pieces of information. Okay, so you saw in the first example, they gave me the reaction, and I pulled the half reactions out. This time, they give me the two half reactions, and based on those values of the reduction cell potential, with the more positive value indicating the cathode, where reduction is happening, I can identify it that way. Now, at this point, like I mentioned before, if this reaction here is actually an oxidation reaction, well, then it's written incorrectly, right? So I need to then flip this reaction around to show an oxidation reaction, which means that I would have a Ca solid producing my Ca2 plus ion plus my producing my 2 electrons. Again, oxidation is loss of electrons. Okay, so that's now my half reaction, which will be important when I have to write my overall balanced reaction. Okay, so I think I've pretty much answered a lot of these first two questions here in A and B. So my balanced overall reaction is going to be Ca solid plus Cu2 plus aqueous yields my Cu solid plus Ca2 plus aqueous. Okay, now it's time once again to calculate my cell potential, and again that's going to be the cathode minus the anode, so I know those values. Oops. Minus 2.868, and I get a cell potential of 3.208. Once again, that is positive, so this is another spontaneous redox reaction. Okay, that's all we're going to cover as far as galvanic cells and cell potential. So now I get a chance to do some practice.